So in this video, we are going to introduce the concept of polarization, which tells you something about the direction of the electric field and magnetic field inside a propagating uniform plane wave. So we got 3 parts to this lecture. We're going to talk about linear polarization. The next, we'll talk about circular polarization, which involves a spinning electric field. And finally, we'll talk about some places in nature and science and engineering where polarization comes up and appears. So let's start off with linear polarization. So when we introduced the wave equation and we introduced a uniform plane wave, to make the math a little more convenient for us, we assumed that the electric field would be in the x direction and the magnetic field would be in the y direction, and the propagation direction was in the z direction. So the electric field crossed with the magnetic field equals the propagation direction, and all 3 were perpendicular to each other: electric field, magnetic field, and the k vector. They were all perpendicular to each other. But that's not necessarily true in general. We really could use something more general than that. And so that's where we're going to get into a discussion of polarization. So I'm going to orient an axis like this. Let's say you've got the x-axis pointed up and down here, and the z-axis is pointed to the right. And in this case, the y-axis is pointed out of the page, since x cross y must equal to z. So we know for a fact that for a uniform plane wave, if we have the electric field in the x direction and the magnetic field in the y direction, then the direction of propagation will be z. However, we could just as easily have a situation where the x direction represents where the magnetic field is. In other words, I'm going to draw 2 different types of polarization. The first is the electric field is in the positive x direction. The magnetic field is in the positive y direction, in which case the direction of propagation, the k vector, or if you prefer, the pointing vector, is in the positive z direction. Let's get rid of the k and keep that as an s. So that's one way to orient the wave. But let's see, because there's another way we can do this. What if we had the electric field in the positive y direction, or the magnetic field in the negative x direction? If we do that, then the pointing flow will be in the direction of E cross H, so y hat cross minus x, which is also the positive z direction. So here we have 2 uniform plane waves, both directing their energy in the same direction, but for each, the electric field is pointed differently. One, the electric field is up and down. The other, the electric field is side to side. Whichever is the electric field, the magnetic field is the opposite way. And these are 2 different polarizations, both of which we're going to call linear polarizations. And they're called linear polarizations because the electric field, there's a line for the electric field, and no matter where you go up and down the propagation direction, the electric field is always pointed in the same direction or along the same axis. It can go back and forth along that axis. So let me show you what this looks like pictorially, but first let me just sort of define what these mean. Number 1, we would call this linearly polarized. Let me draw that a little better. We would call item number 1 linearly polarized in the x direction. All right, when we talk about polarization, we're by definition referring to the direction of the electric field. So number 2, we would call that linearly polarized in the y direction. Right, so these are both linearly polarized, but there's 2 different forms of linear polarized. There's x and y, and we could also have everything in between. We could have the electric field be at a 45-degree angle between the x and the y. So we could also have an electric field that's pointed this way. Wait, sorry. We could have an electric field that is x hat over square root of 2 minus plus y hat over square root of 2. And we could have a magnetic field, which is x hat over square root of 2 minus y hat over square root of 2. Sorry, it was supposed to be a magnetic field here. And that would also be a linearly polarized wave, but the electric field in this case is at a 45-degree angle between the x and y axis. You could look at it as a combination of linear polarization number 1 and linear polarization number 2, right? Add those together, and this is basically what you're going to get, right? This basically equals 1 plus 1/2 of number 2. Right, if we combine number 1, I should say minus 1/2 of number 2. Sorry, minus number 2. Right, we take number 1 and subtract number 2, then we're basically going to get this new polarization, which again is a 45-degree angle between the x-axis and the y-axis. So there's infinite number of linear polarization because the electric field can be pointed in any such direction. If we take a plane that's perpendicular to the direction of propagation, the electric field, like a clock, can be pointed anywhere around that circle that's within that plane. So let me show you this visually. Right, this represents a linearly polarized uniform plane wave. And the diagram on the left shows our visualization of what a plane wave is, that at any given plane that's perpendicular to the direction of propagation, everything along that plane is constant. The electric field is the same, the magnetic field is the same. You can slide along anywhere along one of these planes and nothing changes. You will have no idea where you are. And that plane is perpendicular to the direction of propagation, importantly. On the right is an example of what this actually looks like when the wave is moving. And I'll caution you, in this diagram, the propagation direction is in x, whereas in the whiteboard a minute ago, it was in z direction, but it's still the same qualitatively. But what you'll notice is that the electric field is pointed in the y direction. So anywhere you go, you're going to see the electric field vary from positive y to negative y, from positive y to negative y, whereas the magnetic field, which is in red, is along the z direction. So this is linearly polarized because no matter where you go, the electric field can only have a y component. There's a single line that we're confining the electric field to exist on. And so that's a definition of linear polarization. Again, that the electric field could be pointed any such way in the YZ plane in this diagram. And the magnetic field would be whatever direction it needs to be in order to assure that the electric field across the magnetic field equals the direction of propagation. So that's linear propagation. And we're going to move on next and talk about a more complicated form called circular polarization, which actually has some very interesting applications we're going to see in part 3 of this video.